compatriotas mexicanos, en español a Raúl. And I say hello to all guys that are there. I really want to be there, but I had a health problem with my mom, and I can fly to there. But okay, this is the presentation. A few months ago, when Raúl was here in Tucumán, talking about the space and radiation and the guitar play and the assault and other stuff, I said about that we make a little satellite here in Tucumán. And he told me, okay, good idea to present in Mexico in the next SERESSA and December. I think it was on October, I think. Okay, I'll give you a little introduction about us, where are from and what can do here. I suppose that it's moving. Okay, it's Argentina, and we are 100 miles to the northwest of Buenos Aires. When the tango was born, not in Uruguay, it wasn't in Buenos Aires. It's the most little province in Argentina, but we are 2 million people. In a little town. Our company is Tucumán BBS. BBS is like a bulletin board system. We are really old company. We born in 1987. Okay, the last century. And we start with the bulletin board systems in the university. Internet doesn't exist at those time. We give telecommunications in the north of country, and our main area it's Tucumán. It's our province. The last year we made a deal with San Pablo Tucumán University. It's a private university in Tucumán. It's the newest university. It's 8 years old in Tucumán, but they have a new style to think about how to make the things and how to study and learn. Okay, this is our center. It's brand new. It's have just only 1 month. Okay, when Raúl was here, we building at this time in October, but it's working now, and it's on the campus field in the university. It's a really nice place. The big trees, big fields, nice to work. Okay. Well, this is pictures inside the laboratory on the day we start. We was the first ISP, Internet Service Provider, at the northwest of the country from 1995 commercially, but I started to develop the BBS on the 1985, 86. Well, about the was talking with Raúl. How can use the space? How can the civilian guys how can use the space technology and the space, because that you know the main use of the space was military, okay, and commercially, now with the big company. And we try to think how can do it. We thought about maybe the solution was democratize the use of the space, but democratize was a lot of millions of dollars to use, and maybe Raul have, I don't have it. And okay, we can do how to do it to use the space with the civilian use. The traditional space industry use longer schedules and a few missions. Okay, sometimes a mission have 5 years, 10 years, a longer schedules, a lot of people, a lot of expensive people. Okay, the big buildings, all stuff of the kind of industry. It's big, expensive. How? Because okay, if I spend a lot of money, I must demand the higher reliability. Okay, I be sure that the piece of electronic, the piece of metal that I will put on the space, I be sure that it must be work, must be work, and it's a higher cost. Okay, a lot of money, a lot of $1 million, maybe $1 billion. But we have a COTS industry, that it's a customer of the shelf. When you buy it, the old-fashioned guys, we went to the electronic partner and buy electronic circuits, resistances, transistors, and batteries. Now the young guys use the eBay, no, and put on the eBay and both and buy all that stuff that they need. The difference between that industries is with the COTS industries, we have a shorter schedules and we can make more missions. Okay, we can accept to fail in the first missions. We can accept to destroy the electronic, to fail a different kind of parts of the satellites. It's a possible. Okay, it's a part of develop of this kind of satellites. The difference is you have a little demand for the higher reliability. I think it's the main difference. When I think the cost, maybe the university can assume to spend $1 million to make a satellite. The NASA spent $400 million. The DirecTV spent $1 billion to sell the DirecTV signal to the 1,000 million people. Okay, we reduce the demand for the higher reliability. Is the maybe the most important difference between both industries. It's a lower cost. Simple. The COTS industry. This is the cycle of the COTS industry. When you compare with the traditional space industry, higher cost to lower cost. In the 1995, some guys in the in Polytechnical in California think about the nanosats. Nanosats, it's have lower than 10 kilograms, the little piece of metal, and it was a really good idea. This is I think it's a EtubSat. Maybe it's one of 300 nanosatellites that is still working in the space actually. It's just only one. Okay. Where live the nanosats? If I talk about something that you talked in the previous presentation, that please tell me, because when I don't know what you said there. Okay, don't problem about this. Okay, where live the nanosats? Okay, they have our world, and the Van Halen. Van Halen is a good shield for us. Maybe we can live here because the Van Halen exists. If we see here, I don't have. If you see our no, okay. Well, the nanosats live really near to the Earth, just only 230 miles over our heads. Really near to the International Space Station. It's 600 between 350 kilometers to 650 kilometers. This is the area where the nanosat lives. At this orbit, without thrusters, maybe the satellite can live between 6 to 24 or 35 months, and then go down and just burn out when it get our atmosphere. Okay, but it's a harsh environment. Okay, it's really harsh. The first stage is when I put our nanosat on the vector, on the from the Earth to the orbit, maybe 40 minutes to 4 hours, depends which vector you use and the way to put on the orbit. It must survive the G-force, okay, the tremendous G-force. I put it big, the big image to get a smile from you. The G-force maybe 10 G-force, 12 G-force, okay, and for example, high level of sounds, maybe like your kids when put the ears with the phones and hear the music inside the head, but you can hear outside the head. Imagine this one. Okay, and the vibration. The vibration, it's a big problem too. If you don't have a really nice metal structure or body on the satellite, it's destroyed, really destroyed. And the next, when the vector it's outside in the orbit, you have some different kind of problems. The first is the vacuum on the space. The capacitors, the boards have a huge problems on the space to the vaporize the different kind of liquids. If you don't really prepare first at the earth, the boards on the satellites. The other problem, and it's a really important problem, is the thermal amplitude. The nanosats have an orbit, one orbit on 90 minutes. Have a complete orbit every 90 minutes. It seems like you have 45 minutes of light, 45 minutes of night. And it's think that you have maybe minus 40 Celsius degree and have 120 degrees every 45 minutes. Imagine that thermal amplitude is really hard too. But I think the bad words on the satellites is, I think that Raul like it. It's radiation effects that you like talking about the radiation effects. I don't tell you about the radiation. I just only mention it. The TID, the total ionizing dose, LAT, and maybe the single event effects. I know that you talked on the last years about this one, and I suppose that you are really you know really about this, the single event effects. Just I only mentioned the single event upset, the latch ups, the functional interrupts, the burnout, and the gate ruptures. If you wanna talk about this one at the final of the presentation, we can talking about this. You hear me because I don't hear anything from you.
Yes.
Okay. Okay. This is a summarize. This is a summarize of the radiation effects that can destroy the nanosatellites. Okay, how to do it about this one? We think about the FBC. What's mean FBC? Faster, better, and cheaper. I'm a CEO of company. I think all days about the FBC. Faster, better, and cheaper is the way to grow, to make it grow our company. And we think how using the COTS, customer of the shelf. It's a nice idea from Raul about the presentation. Where using that I told you about the Cali Poly, the California Polytechnic State University, and the name was the Nanosats. The Nanosats. This is a picture of the Nanosat, the one unit. This is the scaffold. This is the body of the Nanosat. It have the CubeSat specification. One unit. It's a 10 per 10 per 10 centimeters, and it must have a minus no more than 1 kilogram. This is a Calipol specification. But you can use the 2 units, 3 units, 4 units, or 5 units CubeSats. You can adding CubeSats to 10 per 10 per 50 centimeters. Okay, I don't know if you understand the idea. If you remember the first picture that I showed you, the nanosat, it was 3 units. This is an example of the 1 unit CubeSat. On the top, it have a camera, and in the middle, I don't know if you can see the batteries, and on the bottom it's have an OBC that we're talking about now. Okay, I'll show you an specification: the CMOS camera, the sensors. Some CubeSats have passive magnetic stabilizations. It's really simple. It's just magnetic. It's a magnetic part. If you put it the north of the magnetic part, the satellite, when cross the south pole on the Earth, put the camera looking for the Earth. On the another side of the Earth, the CubeSat turn 180 degrees and looking forward to the space. It's the most simple stabilization. And I have a power board. Maybe sometimes the power board is just simple that have a battery and some kind of circuit to control the charge of the batteries, and on the bottom have an onboard computer. And another important part is it's a transceiver. It's to communicate to the Earth, to say us about the satellite health, to send the pictures, another stuff. Okay, about the core of the nanosat, it's an OBC, an onboard computer. The typical function of an OBC, it's have an DC-DC power conversion. The board get the power from the solar panels, sometimes 3.7 volts, and put on the DC power conversion and charge the 5 or 7 volts batteries, and it's give to the rest of the satellite the regulated voltage. Sometimes 3.7 volts and 5 volts. Maybe it's the most important is 5 regulated voltage. Sometimes use 12 or 18 volts. It depends how to design the board. Another important function of the OBC, it's ground telecommand decoding, with the ground station, with the VHF or UHF or microwaves. We can send the commands to the satellite to configure, to shut down, to reboot, to reorganize the satellites if some parts have on a failure. Another function is packet telemetry formatting. The board gets all information about the satellite, like temperature, like voltage on the panels, like voltage on the batteries, inside temperature, outside temperature, and put on the telemetry format and sent to the Earth using the transmitter. Some normally use the VHF or UHF transmitter. Sometimes the OBC can auto-reconfigure the board and the nanosatellite if it's have some kind of file with the sys, for example, with the latch-up or another failure. Another important is that I told you about the housekeeping telemetry. Housekeeping is the health of the satellite. It's the other function. It's manage the input-output modules like cameras, like LEDs. If you use the LEDs to make beacons, lighting beacons. If you have more big satellite, you can deploy the solar panels. This is all that output modules. And the other function, it's an attitude control and determination. Sometimes on some satellites, not all, it's important to keep the satellite quiet in the space. It's moving 28,000 kilometers per hour, but you must keep quiet on the orbit. For example, to get the pictures. If you wanna get a picture of the Earth, you must be sure that the camera it's looking to the Earth. When the vector put out the satellite and on the orbit, it have an spinning. Okay, and if you need a stabilize, you need an attitude control. The attitude control, you can use the magnet torquers, the torque wheels. Is kind of different solutions to stabilize the satellite. And another important part is the determination. Where is the satellite using the GPS? You remember that the GPS it's on 25,000 miles over the Earth. It's a higher orbit, and you can use the GPS constellation to locate our nanosatellites in the lower orbit and the lower orbit. It's most common useless. Okay, for the OBC, I know that you're talking about the FPGAs and the microcontrollers, microprocessors, and the memories. Our choice was the microcontrollers. Okay, we think about this the better option to make a satellite. Why? Our project. Okay. The samba. It's a thing that Raul playing in the guitar. The specification to our Samba 1 nanosatellite, it's a 1 unit satellite size. It's just only the demonstrative satellite. It don't have a payload. It's entirely designed with the COTS component. I bought a couple of blocks of my office. It have 4 solar panels that it can get 1.7 watts from the sun. It have just only one integrated OBC. It's the OBC have DC-DC converter. It managed the batteries. It's managed the housekeeping, telemetry. It's make AX25 codification to transmit the telemetry. It don't have an ADCS. Maybe it's still spinning on the orbit. Is no problem for us. Just only put it the magnetic piece of metal to try to reduce the initial spinning. It have 4 watts nickel metal batteries. It's really near to the cellular phones batteries, and it have an receiver on FM on the 434 megahertz, and it have a downlink to transmit us the housekeeping information on the 2 meters transmitter on FM2, and it have another transmitter on 2 meters too to send the Charlie Whiskey or beacon. Is a Morse code transmitting the identification. And we investigated the light Charlie Whiskey beacon to send the failure codes. We think it's reading about the nanosatellites. The most important failure on the satellites, it's the OBC and the transmitters. I don't know really why, but the most important failure is the transmitters. For this reason, we think about to make a lead beacon. It's a light beacon. How it works? Normally, the satellite cross our sky and lighting on, lighting off for the 10 or 20 seconds. You can transmit on Charlie Whiskey on the Morse code the failure code. How? Using the big guys, the old guys there that understand me, the bulb camera. It's when you still open the photographic camera, getting the sky, you can get the transition of on to off light of the satellite, and it was a Morse code about the failure code of the satellite. We're investigating about this. This is a picture of Samba 1. It's have an aluminium skeleton. It have 800 grams. On the upside, it have LEDs, and on the sides have solar panels. It was the first stage of to build, and using the CubeSat design specification from the California Polytechnic State University. I don't know if you can see in the paper. This is the solar panels. This is the most simple DC-DC converter. It's an integrated it's get the solar panels energy and charge the batteries. And this is the first version of the OBC. This was the first version. It was the second version. It was the third version. And it's we make layers. On the first layer, bottom it's battery. The second layer it's a DC-DC converter, and the third layer it's an OBC. It's another image. Look at the first version used the Samsung battery of the cell phone. This is the controller. Okay, it get the signal from the receiver and translate this radio signal to the telemetry, to the software here, on the app of the picture. You see the signal, the transmitter, and if you look at the frequency, 437 megahertz, receiving the telemetry. It's just only to get the telemetry, and on the left side you see the telemetry values. Okay, this is the picture again. About the COTS, between COTS to space grade components, it have a brief resume about this. The COTS, the standard COTS components, it can work between minus 45 to 85 Celsius degrees. The other option that I think is the better option, it's the enhanced performance, where you can track the how to make a process. It's have a special mold compound. It's like when you use the Toyota Prius, or you use the Camaro maybe. And it's have a little extended temperature between minus 55 to 125 Celsius degrees. The next is military grade. It have a ceramic package, the circuits. The temperature, it's the same, but it's more strong to the G-force, the vibration, and other problems. And the space grade to use on the circuits, it's minus 55 to 125 Celsius degrees, but this is the most important. It's guaranteed on 10 years. The circuit must work without failures 10 years, moving between temperature amplitude. And the guarantee at the 95 Celsius degrees is 15 years. Is the most important part. The cost between the COTS to the space grade, maybe 1,000 times. If you buy an amplifier, the COTS amplifier, maybe 70 cents. If you buy the same space grade amplifier, maybe $2,000. This is the relation. And another important part is the builder guarantees about the radiation specifications. Maybe this is the most important part. Okay, this is a briefly version that I told you about it, the version 1. Hello?
We're here.
You still
Yes.
seeing me? Okay, because I don't see. Okay, you hear me? You can hear me?
Yes, I can hear you.
Hello?
Hello?
You hear me?
Yes,
Oh.
fine, perfectly.
Okay, but
Continue.
I don't see you. Okay, the version 1.0 was a single processor. It's have a single EPS. Tell me when can I continue. Hello?
Sí, sí.
A ver, Luis, ¿me estás escuchando? Hola, hola, hola. Bueno, entiendo que me están escuchando, así que voy a continuar. Yo los veo muy mal a ustedes. Okay, well, I told you about the first version. It's have the Samba one. It's have a single processor and a single EPS, simple DC-DC conversion. The communication system was an autonomous board, and it have a simple watchdog to check the functionality of the board, and the expectancy of life just only 6 months. If the Samba one live 6 months in the space, we're really happy. It's just only our expectancy with the COTS components. Inside, it just only have solar panels. You can looking for the next slide. Okay. Well, on the next slide, you can see how it's work. It's have the same. It's have solar panels, the EPC, the DC-DC converter, the batteries, more batteries because it use more energy. And it have three CPUs. This is the most important difference. It have the 3 CPUs running the same program. Running the same program at the same time, and use another microprocessor voting the CPUs. Each time the vote check the CPUs on the I2C bus and check that the 3 CPUs have the same state. Okay. And it have a transmitter, it have a receiver, and have 2 temperatures sensors too, outside and inside. It's really important to the batteries life. Okay. And it have a software watchdog too on the vote. You still hear me?
Yes.
Okay. I lost you. Okay.
Worst here, who's the worst?
Okay. The slide was changed?
Yes. No, it hasn't changed.
Okay. I called to my internet company.
No, it's not the one we want. How to check SEEs?
Okay, right. Okay. Well, you know about the SEEs. Okay, I don't tell you anymore about this. Maybe it's the most important failure of the satellite.
Continue.
Okay. You can see the simple diagram about you seeing the diagram?
Yes.
Okay. The simple diagram about how to check the CPUs. The CPUs running the same program at the same time with the same clock is really important. It must use the same clock to synchronize those CPUs. And the hardware watchdog checking the outputs, some outputs of each one of the CPUs. And if the hardware watchdog check a difference between three CPUs, put it a pulse on the output 1 and reset the CPUs and restart the system. This is the most simple watchdog function on the most simple nanosatellite. How it's work? Just only check the microprocessor, check the inputs, and every cycle make a pulse on the physical output of the micro. Send a pulse to the watchdog, and then calculate some calculation like temperature, like battery status, like other stuff. Don't problem, and make an output if they need make some output. Send a telemetry to the hearth, and the process start again. Inputs, pulse, calculate, output, telemetry. It's a cycle. You can see the both slides.
Yes.
Okay. This situation, I think it's Apollo 13. Houston, we have a problem. Okay. On the below of the slide, you can see the pulses of each microprocessor, sending the pulses to the watchdog. This is the normal status of the system, and the reset it's still on off, on 0. In case of failure, for this example, the microprocessor 1 have an event and fail. The watchdog detects that the microprocessor 1 don't send a pulse and detect the abnormality, detect the error, and send the reset to the 3 microprocessors, and the system reboot. Fail and reboot process. If how can you, I don't see you, please. If you lose on some time, just tell me, because I'm driving with my eyes closed, okay? Okay, I don't know which slide that you use it. Okay, this is the cycle of the multiple CPUs Nanosat board. It have 3 CPUs. It have a common I2C bus, and it have a both hardware and the software watchdog. And to the right side you have the cycle. Inputs calculate, and every time the results sent to the software watchdog to compare the result of calculations. Okay, 2 plus 2, it's equal to 4. It's CPU 3 is 3. Okay, it's a failure, and make an reset. I'll show you the flowchart diagram. Okay. You seeing the next slide? The flowchart. Okay, right. Okay, this is the flowchart of the watchdog. Each CPU calculates some calcul, just like simple 2 plus 2, or another calculation like sensor temperature or battery status. Okay. The CPU send the result to the watchdog, and the watchdog compare 3 results. 3 results are equal. Okay, if yes, okay, it's a good. The next step is send the random number or the random data to the random memory area. Okay, the free area, memory area. Put the number or the data on the same place of the memory of each processor. Okay, write the data, and then read the data. If the 3 reads are the same, the health condition of the system, it's okay, and the system is still running. If not, the software watchdog interpret that some data was corrupt and reboot the system. And you can use or not on the both system. For example, if the processor, the microprocessor 1 and microprocessor 2 have the same data, okay, it can think about the microprocessor 3. It's having a failure. you can put out the processor or try again resetting the system. It's different kind of specifications. Sometimes if you have more of 10 failures on the same processor, okay, the microprocessor, the system interpret that it's corrupt and get out, and the system is still running with 2 microprocessors. Okay, this is the complete slide. Tell me about the time. Is right or I put another gear?
5 minutes.
Okay. Okay. Good. This is the wide vision of the system. The next, again, the faster, better, and cheaper. How can do it faster, better, and cheaper with this thing? We learn about the successful cases. I told you about actually we have more of 300 nanosatellites running on the space, and we think and we believe that we can use the COTS component on the space with successful cases. This is the UGNU. This is the 3 units Indian nanosats. It was launched on October on 2011. It had an infrared camera. It's entirely made with the COTS parts. It had minimal redundancies, just only 2 microprocessors running synchronized, and the expectancy of the life was just only 1 year. It's still running, and it's have 4 years. It's really successful. This is another. This is the AAUSAT 3. This is the 1 unit, the CubeSat. It have a software-defined radio to check the radio waves coming from the Earth to the space, and check the automated ID systems. It's that the system to check the planes. Okay, I don't remember the transponders numbers of the planes. It's trying to check from the space the planes. It was launched on April on 28, and it was working to October of the last year, and the expectancy of the life was 1 year, and it's work 6 years. And in this case, it was really interesting because we can check the reason for the satellite had a failure. The OBC doesn't fail, the battery failed. We can check on September how the voltage of the battery goes down. On 7 days, the battery goes down, and the satellite did. But the onboard computer was run. And I think the most amazing COTS part, it's running on the space. This is I'll present you a PhoneSat. You seeing the satellite? Okay, right. I have a big delay. I think this is the most important COTS satellite to demonstrate that we can do it. This is the PhoneSat. The PhoneSat made with it have two nanosatellites, the Graham and Bell PhoneSats. This is the names. Those are the names. The PhoneSats is still operating in orbit and may prove the lowest cost satellites even flown in space. The goal of the NASA PhoneSat mission was to determine if a COTS-grade smartphone can be used on the main flight of avionics or capable to yet very inexpensive satellites. It have a Nexus inside, the Google Nexus phone inside. The board, the onboard computer, it's a phone running a phone board and running the Linux system. All stuff inside is a phone. The hardware for this mission you see in the next slide? Hello, Luis. You hear me?
Sure.
Okay. The hardware for this mission was the Google HTC Nexus One. It's a phone you can both on eBay and pay at $500, and it's running an Android operating system inside. The expectancy of flight was 3 months, just only 3 months. It's still running. It's have 15 months running. The cost was $3,500, and the autopsy of the first PhoneSat that it was did was the batteries again. I think the most important failure with the nanosats or on the space, it's batteries. The main cause of fault it's a battery. On resume, we think about the COTS in the space. It's a reality. We can do it. We can use the COTS components. We can make satellites and put it on the space. If we have an expectancy of 18 months, I'm sure that I can use the COTS component to make a good mission. For example, to get a picture of the hertz, a high resolution picture of the hertz, an infrared picture of the red of the hertz. We can use to get a radiation on the different altitudes of our space, and it's a good idea to use on the universities for the little companies like us. We have a good. We think we have a good future with nano satellites. For this reason, we are working really hard about use a different kind of COTS parts and have a different kind of experience about the nano satellites. We expect have failures and some, maybe the 2 or 3 first nano satellite put it on the space, it will fail. We expect this, but we think about on the next missions from the 5th mission, we have successfully missions. We're working on the Samba. We're working to put the first payload, and it will be an infrared camera to check the fields. Okay, to check the fields in our country. It's our goal in our country, and I think and expect to work with Raul or some guys that are there on this project. It was our first idea to was there with you, but okay, I can did, but I still running on the project. Thanks, guys. I expect that you enjoyed the presentation. It's a little difficult on this kind of communication, but if you have questions, okay, I here to respond us.
Thank you very much. Question? Oh. You listen?
I can't hear you. Okay, the cost of the project, we estimate the $40,000, include the vector to put on the space, from using the Kazakhstan and Russia vectors is more cheap than an American or European vectors. It's most dangerous maybe, but for the cost of the first stage of the project, I think it's a good idea. Use this vector. Okay, bye bye, take care and enjoy it. Thank you.